It is my pleasure to introduce Bishal Deb from University College London, and he will be presenting on total positivity of the Eulerian triangle. Go ahead.
Right. I would like to begin by thanking the organizers for giving me this opportunity to speak at this GSCC. So about this, so this work was mostly done in the past 1 year, and I'll begin. But only thing I'll say is, if you stick around, there are a few memes towards the end. Okay, so a matrix of real numbers is said to be totally positive if all its minors are non-negative. Or in other words, the determinants of all finite square submatrices are non-negative. So here we think of a matrix as an array of numbers and not as a linear operator, because this definition is very basis dependent. And note that in my definition, I have said nothing about the matrix being a square matrix. We only want the determinants of the square submatrices. In fact, we can even have infinite matrices, and as you will see in a while, that we will be working with doubly infinite matrices. And later we will upgrade from matrix of real numbers to matrix of polynomials. So this was first defined by two different groups in the 30s. So Krein and his group, they were looking at some mechanical systems, and Schoenberg and his group, they were looking at some problems from analysis. And we use Schoenberg's terminology, and I say that, so I stress this, that if you are looking at any of the relevant literature, please note what is the definition of total positivity. And by totally positive, I mean that the minors are non-negative, not strictly positive, non-negative, because depending on who the authors are following, they could either be following Krein's terminology or Schoenberg's. So we use Schoenberg's terminology, and totally positive refers to minors being non-negative. So an example of TP matrices are bidiagonal matrices. So these are matrices where two consecutive diagonals have possibly non-zero entries, non-negative entries, and all the other entries are non-zero, are zero. And matrix sum does not preserve TP. And one can come up with an easy 2x2 example. However, matrix product preserves TP, and this can be proved by using the Cauchy-Binet formula, which basically expresses the determinant of a product of two matrices as a sum over products of their determinants, of the minors of those two matrices. So now, right from the beginning of when total positivity was defined, it had applications to several areas in mathematics as well as other fields. Particularly in combinatorics, its study was started in the 80s by Brenti, who was looking at some of the properties which Federico spoke about yesterday in his talk, which is like unimodality, log concavity, etc. Many important combinatorial triangles are TP. So by that, I mean that if you have a combinatorial triangle, you can write them out as matrices, and a lot of them are totally positive. Some of the examples are the binomial triangle. So the entries, so at position n comma k, you have the binomial coefficient n choose k. The Stirling cycle triangle. So these consist of the Stirling cycle numbers, or the Stirling numbers of the first kind, which basically are permutations counted by their number of cycles. The Stirling subset triangle. So these are the Stirling numbers of the second kind, and these are set partitions counted by the number of blocks which they have. Now, if you have, so all of these are lower triangular matrices, and if you have a lower triangular matrix, infinite lower triangular matrices, if you have a lower triangular matrix, what you can do is you can take each of the rows and then reverse them. So you can obtain the reverse. So you can obtain the reversal of each of these matrices, and it was shown that, so Brenti showed that the reversal of the Stirling cycle triangle is also TP. However, reversal in general does not preserve TP. So one can construct an example. So this is not an operation that preserves TP. Let's look at some of these triangles here. So the reversal of the binomial triangle, that's just the binomial triangle again. The reversal of the Stirling cycle triangle, I've said that that is TP as well. How about the reversal of the Stirling subset triangle? So we looked at it and we conjectured sometime in 2019 that this matrix, so we have a shift in some of the parameters so that it becomes a lower triangular matrix. So we conjectured that this infinite lower triangular matrix is totally positive. Another triangle that people have looked at is the triangle of Eulerian numbers. Let me quickly define what they are. So you can define the descent of a permutation sigma to be a position, as the name suggests, a position I, such that sigma of I is bigger than sigma of I plus 1. So and let des of sigma denote the number of descents of sigma. So in this example, so in this example, there's a permutation in one word notation, and the letters in red denote the positions where there is a descent. So here there are 5 descents. And the Eulerian number nk is defined to be the cardinality of the set of all permutations on n letters with k descents. And these are the first few rows of the Eulerian triangle. And Brenti in 96, which is like 25 years back, conjectured that the infinite lower triangular matrix of which is the Eulerian triangle is totally positive. And we have verified it for the upper left 512 cross 512 submatrix using an efficient algorithm which produces bidiagonal factors. However, the bidiagonal factors which are produced have rational numbers with large denominators, and a general pattern is not clear. So it's not easy to guess how one would prove it for the infinite matrix from by looking at bidiagonal factors of this matrix, of the finite cases. So let's look at both of these triangles. So you have the Stirling subset triangle, which I spoke about, and also the Eulerian triangle. Now, the interesting part is both of these triangles can be generated by using some simple recurrences. And if you observe the two recurrences carefully, you can see that there's just an extra k term. There's an extra k here which is missing. So this just suggests that one can introduce variables. One should be introducing variables so that you turn some of the variables on, you get this, and you turn some of them off, you get this. And but if you have variables in your recurrence, you're going to end up with a matrix of polynomials. So what does total positivity even mean there? Well, a matrix of polynomials with real coefficients is said to be coefficient-wise TP if all its minors have non-negative coefficients. So the minors of this matrix are going to be polynomials themselves, and we want the minors to be to have non-negative coefficients. And again, I say nothing about the number of, I have no restrictions about the number of variables these entries can have. So there can be one or several variables. And if you substitute non-negative values into these variables, you're going to end up with a matrix which is totally positive. So this says that coefficient-wise TP implies point-wise TP, but it's a much more stronger property. The reverse implication is not true. So what we do is we take these recurrences and we introduce some variables A, B, C, D, E. So you can see, so we introduce 5 variables, and with certain substitutions you get the first one, and with others we get the second one. And we conjecture if it is coefficient-wise TP, that is, the minors are polynomials with non-negative coefficients. It's a more general conjecture, and if it is true, then it will prove that both the conjectures about the reverse Stirling subset triangle and the Eulerian triangle are TP. So we tested it, and it turned out to be true till 11 cross 11. We did this within a week. However, after about 99 days of CPU time and 2 months of real time, it turned out to be false for size 12. However, is all hope lost? Not really. We have another candidate. So we can put b equals 0, and we obtain this recurrence. And this seems to be true till 13 cross 13, we've checked it. And let's look at some special cases of this. So if you have all four variables set to 1, or these three variable so these three variable cases where one of the variables is set to 0 and the other three are set to 1, all of these give you the some version of Eulerian triangle or shifted Eulerian triangle. So if you prove that one of them is TP, you get the other two are TP. If you take this two variable case, then you get the binomial triangle, which we know is TP. If you take this other three variable case, you get the Stirling subset numbers, and its TP was proven by this was proved by Brenti in 95. The only other three variable case that remains is that of the reverse Stirling subset triangle, and that is what we have conjectured. So, well, I did promise a meme. Here's one. So we have upgraded from a matrix of numbers to a matrix of polynomials. And now, well, what we did was we looked at this three variable case more carefully, and actually it's no longer a conjecture, and we've managed to prove it. In fact, we have proved it not just, so again, I'm just, these are just the first few rows of the reverse Stirling subset triangle again. And in fact, we have not just proved it for the pointwise case, but we have it for, so you just take ACDE triangle, this is what we call it, and you put D equals 0. And so here, if you put A equals C equals 1, you get back the reverse Stirling subset numbers. So, so the entries here can be thought of as counting set partitions with certain weights. And we have three different proofs. So we have two digraph proofs which use the Lindstrom-Gesell-Vienno lemma. So one of the proofs, it shows a bijection between paths in the digraph to set partitions. And the other one, it exploits the structure of the digraph and proves a certain recurrence, which all these entries also satisfy. We have a third proof, which is an algebraic proof that we call the quasi-production matrix method. And I will quickly show you what the digraph is. So this is the digraph, and how much time do I have, if I may know?
About 3 minutes.
Okay, great. So then I can maybe mention what the Lindstrom-Gesell-Vienno lemma is. So, so here, so we have this directed graph. So I'm going to tell you what the Lindstrom-Gesell-Vienno lemma is. So take a directed graph with some weighted edges, such as this one. So here I have color coded the weights. So all the black edges are weights 1, and the green ones are A, the red ones are C, and the blue ones are E. So take this directed graph. Now you have two special family of vertices. So the UIs, which we call the sources, and the VIs, which we call the sinks. You can now each of the weights are the edges are weighted, and we can also define the weights of a particular path. So let's say you have a path from vertex U3, starting at vertex U3 and ending at vertex V2. Then you define its weight to be the product over all the weights that you encounter on the way, product over all the weights of the edges that you encounter on this path. And you can construct a matrix called the transfer matrix, where the entry n comma k is basically the weighted sum over all paths from source n to sink k. Now the Lindstrom-Gesell-Vienno lemma says that the determinant of this matrix is basically a signed sum over non-intersecting lattice paths on this graph. And the way we have oriented the edges, where you have edges either going down or to the right, you can only have, so the way we have a planar digraph, and the way we have oriented the edges, it ensures that what we get from the Lindstrom-Gesell-Vienno lemma, the LGV lemma, these are not signed sums, but these are actually sums, just a sum. So there are no negative signs. And so we get that. So if we know that the transfer matrix of this matrix is basically the ACE triangle, we know that the determinants are given by tuples of lattice paths. And that shows that the determinant is non-negative because because these determinants are a sum over stuff which is non-negative. So and we have a bijection which given if you give me a path from this from starting at un ending at vk, then I'm going to obtain a set partition with since it's a reverse, so there's a bit of indexing. I mean, since it's the reverse Stirling subset triangle, so it's a set partition on n plus 1 elements into n minus k plus 1 parts. And finally, I would like to say that we have even further generalizations. So we begin with the Eulerian triangle conjecture, which is a matrix of numbers. Then we go to a we have a 4 variable candidate, which seems to be totally positive so far. We in fact have a 6 variable candidate, and we have strong reasons to believe that even this is TP. And in fact, we have an infinite variable candidate where we take this 6 variable and we replace so you have a term dk plus e, so which is affine in D, we just replace it with summation di. And so these are our candidates, but even the first one, that's still open. The Eulerian triangle conjecture is still open, and one way to prove it, if you would like to prove it, then all you have to do is construct a diagraph whose transfer matrix is the Eulerian triangle, and you will prove the conjecture. And we have been doodling for the past 1 year or so, but we haven't managed to do it. And with that, I would like to say thank you. And I have a picture of how modern day collaborations look like. So these are my collaborators. Right. Thank you.
All right. At this point, let's go ahead and thank Bishal for his talk. Let me just say, if you were presenting for a class and I was your professor, I would give you bonus points for including memes. So way to go for that. So at this point, are there any questions from the audience? Feel free to unmute yourselves or put your question in the chat.
Yeah, I was curious if there is some, early on you said that like a bunch of these combinatorial triangles are totally positive. Is there like a heuristic for why we should expect them to be?
Oh. Right, that's an interesting question. I mean, I can only answer this, that is there a reason we can expect several combinatorial sequences to be log concave? Well, I think the answer is that determinants are also counting something here. So the strategy here is that the strategy here was that we show that the determinant is also counting something, and hence it is non-negative. So I'm guessing that yeah, that's the only answer I can give. But yeah.
Anything else?
Yeah, I can ask it another, which is that when these aren't totally positive, is it typical that they fail on 2x2 submatrices, or do they sometimes fail on like really big submatrices?
Oh,
the determinants are negative.
I mean, well, okay. So we generally, like typically all the experiments that we do, we try and check it for the top left corners, and then we keep growing the matrices. And often what happens is, most of the time what happens is, let's say it goes till, it's true till 9 by 9, or most of the times it doesn't go that far, but let's say it goes till 9 by 9 or 10 by 10, and then maybe in 11 by 11 it's the lower left minor, that's not the entire thing, because, well, the entire thing, you take the determinant, that's going to be non-negative, because that's just product of the diagonal entries. But you just remove the first the 0th row and the last nth column, and so you look at the lower left minor, and that turns out to be yeah, the bad one. But we have no like, we don't know why that happens, but that seems to be the case. However, to answer your question, I mean, I do not know examples where a matrix is TP, as in combinatorial examples. Certainly these things exist, where a matrix is TP2 but not TP3, as in an infinite matrix. No, I do not know something like that. But I think they exist possibly, because yeah, and TP2 is what people call for a certain class of matrices. TP2 is equivalent to what people call strong log concavity. Right.
Great, thank you.
So at this point, if you'd like to continue that discussion, it would be best if we did that elsewhere, because we need to get ready for the next session. So if you want to stick around for session 4 in room D, we'll be starting in about 4 minutes. Otherwise, there are a handful of other parallel sessions that will be going on. So feel free to jump around. Thank you again, Peter and Bishal.
Yeah, thank you, Joshua. Bye.
Mm-hmm.
Here, Bishal, I have a quick question. It's a little,
Yeah,
it's a little selfish. I do cluster algebras, and those came from looking partially at TP matrices, and there's like these total positivity tests. So that doesn't sound as helpful if you're doing something infinite. But have you done anything with looking at TP tests, like this idea that you can test a finite number of things?
Well, to be honest, I do not know anything about cluster algebras, but I do know that. So that's like another. So I mean, I can tell you a bit about the history. Anyways, the answer is no. The short answer is no to your question.
Yeah, I'm not sure if it's helpful for you. And also, since you're looking at non-negative, it might not be as nice because there's like denominators and stuff.
Right.
So if someone's 0, that's a problem.
If you want to look at finite matrices, so there are these class of matrices called Toeplitz matrices, and now for an infinite Toeplitz matrix, you can, so these are construct, if you have a sequence, then you can construct its Toeplitz matrix, and the Toeplitz matrix being totally positive is equivalent to the generating function having certain the poles lying somewhere and the zeros lying somewhere and so on. I have seen a paper where they talk about the finite case. So that's and then they relate it to some Schubert calculus, which I do not understand. So to some quantum cohomology of partial flag varieties, which I do not understand. So this is a paper by Constance Riesch. If you may,
Okay.
maybe interested in looking at.
Yeah.